If I understood correctly, they said we should start in 9 minutes. Or are we supposed to start now?
Not sure. They said 1600 hours their time, our time.
Yeah. All right. So we give it a few minutes.
Okay.
Just that the audience looks right, but
yeah.
If it is okay, we can start now as well. We have the audience ready. So if you are fine starting the talk right now, we can do the same.
what?
I'm ready to go.
So if it is okay, we can start the talk right now. So I will request the chair to introduce the speaker.
All right. So I am Professor Kirsten Jordan. I'm from the University of South Africa. And it is my pleasure to introduce to you the plenary speaker for this afternoon session. At least it's afternoon for us. I'm not sure what the time is for you. Professor Sudan Hansraj is a professor in mathematics at the University of KwaZulu-Natal. His research interests are in general relativity, exact solutions of Einstein's equation, perfect fluids, and astrophysics. He started his career in 1987 as a high school teacher of mathematics. This was, in fact, a standard route for scholastic high achievers of low economic means in marginalized communities in South Africa at the time. Sudan went on to obtain a bachelor's degree in mathematics and then an honors in pure mathematics. And while he served as a lecturer in maths education at a teacher's training college, he obtained a master's degree of science and then a PhD from the University of Natal. His PhD was in general relativity. So in 2002, he was appointed as a senior lecturer in maths education at the Edgewood campus of the University of Natal, which is the teacher training campus. And shortly after that, he was transferred to the mathematics department on the science campus. So Sudan still considers the teaching of mathematics as being one of his most important functions. And for this, he was awarded a Distinguished Teacher Award by his university in 2017. Although he's quite a late starter in research, having first spent a lot of his time as a teacher, Sudan has published over 50 papers, mainly in Einstein's general relativity theory and its extensions. To date, he has graduated 3 PhD and quite a few, about 8 master students in applied mathematics, and he's also supervised 2 postdoctoral fellows. Sudan continues to make extensive contributions to the wider community of mathematics in South Africa. For example, he served with distinction on the Olympiad Committee of the South African Mathematics Foundation for many years, and he's currently serving in the capacity of moderator. During his active term on the committee, he developed various learner and teacher resources and training materials that are still being used. Sudan also served as an examiner of the Interprovincial Mathematics Olympiad, the South African Tertiary or University Mathematics Olympiad. He's a coach of the team representing South Africa. He was a coach specifically of a team for the International Maths Olympiad and also a team leader for the team representing South Africa at the Pan-African Maths Olympiad. When South Africa hosted the International Mathematics Olympiad a few years ago, in fact, that was the first time ever that the International Maths Olympiad was hosted on African soil. Sudan was selected as a jury member. Currently, Sudan is a member of the Assessment Standards Committee of the main statutory body in South Africa that regulates qualifications at various levels. So Sudan, I invite you to present us, please, your talk with the interesting topic of mathematics of gravity. We look forward to it. Thanks.
Thank you very much, Professor Jordan. Thank you also to the organizers, the committee, for allowing me the opportunity to speak at this august BRICS conference. I highly appreciate the opportunity. I know, of course, that I now stand between you and dinner as well, so I'll try to keep myself pointed and within the time limit so that not delayed any further. The discussion for this afternoon is the mathematics of gravity. And gravity is a serious topic that's pursued in various dimensions in terms of physics and also mathematics. So I will mainly focus on the mathematical aspects of gravity, even though it has a connection with physics also. An overview of today's talk is as follows. First, I will explain how Professor Albert Einstein was a game changer in science, and he revolutionized the way science was contemplated in the early 1900s. I'll then give you a brief exposure of the mathematical elements of general relativity, talk about the successes of GR, general relativity, and then discuss the weaknesses of GR. That's where I come in as a researcher. What can we do beyond GR to correct some of the things that are not forthcoming through the general theory of relativity? The answers, I think, lie in higher curvature and higher dimensional analysis. So I will argue that as we go along. And then I will show you how we go about the process of modeling of stars. And that will take us to the end. In nature, there are four fundamental interactions that are well known. We have the weak nuclear force, the strong nuclear force. This is all in the nucleus of an atom. Then you have electromagnetism. These are all well understood. Nowadays, people understand them very well. Maxwell's theorems explain clearly electromagnetic field theory. But the fourth one, gravity, remains to be the most or the least understood of all the four fundamental interactions in nature. There's still considerable speculation about how the gravitational forces or gravitational field works. A major breakthrough in understanding gravity came in the 1600s through Sir Isaac Newton, British mathematician who is arguably one of the finest ever mathematicians. But in his famous book of Principia, Mathematical Principles of Natural Philosophy in English, he contemplated gravity as a force and the famous inverse square law, that the force was inversely proportional to the square of the radius between two objects and directly proportional to the masses of each object. It's easy to guess that there would be an inverse proportion with the radius, but it's another leap of faith to accept that it's inversely proportional to the square of the radius. So that's where Newton's insights came in. You see a little graphic there at the bottom there of the apple falling on the man's head. By now you know the story very well. But as a deviation, the eminent Indian scientist, C.V. Vishveshvara, who passed away in 2017, sadly, and was known as the black hole man of India because of his significant contributions in that area of science. He was a wonderful after-dinner speaker at relativity conferences. And he often told a story of how a coconut fell upon a certain Swami Gravitananda. Obviously, this is a fake information, but the bottom line there was that this guy died as a result of that impact. And he would end off by saying that this was a case of perishing before publishing. And Sir Isaac Newton got all the credit thereafter. But it's an interesting story, which is totally wrong, totally false. Anyway, Newton told us that gravity was a force, and force tells mass how to move. Clearly, Newton's idea of gravity works very well. We still do a lot of work with Newton's laws, and indeed, many of the space missions that took place early on were based upon Newtonian physics. But then came Einstein in the early 1900s, and he unified the idea of space and time. Now the understanding of gravity as a force changed. Now Einstein introduced the idea that gravity is actually the curvature of space-time. It's actually a geometric effect, not a force, a geometric effect. And in 1905, he published the famous special theory of relativity, in which he discussed these aspects. It provided corrections of Newton's ideas at very high velocities. And the famous result, E equals to mc squared, became like folklore in science, but it is a consequence of special relativity. What was new from Newton? Well, in the Newtonian system, we make use of Galilean transformations, which are standard linear motions. But now these are now replaced by Lorentzian transformations. We now rely upon the Lorentz group of motions. And in the graphic, you can see there how what we mean by simultaneous events. It's impossible for three events to be simultaneous, or for three people to agree that something happened at the same time. Why? Because the light from one has to reach the other person in some finite time, and that small amount of time can be accounted for in the special theory of relativity. And so you see that frame of reference changing. When it is like this now, orthogonal, then all three events A, B, and C happen at the same time. But when the frame of reference is subjected to a transformation, a one parameter group of even a linear mapping, we find that the events now take place in a different order. In this instance, C, B, A, see the signal first, second, and third. So that was a great forward move in science in 1905. But that was not all. In 1915, 10 years later, Einstein propounded the general theory of relativity. And this theory of relativity, considered by J.J. Thomson to have been one of the greatest achievements of human thought. Now, just pause for a moment and just contemplate what that sentence means. You know, humans have evolved many different ideas scientifically, mathematically, and so on. But according to Thomson, the general theory is one of the greatest achievements of human thought. It's something conceived entirely in the human brain and which is used to explain natural phenomena around us. It's actually a marvel of mathematical brilliance. The renowned astrophysicist Subramaniam Chandrasekhar, winner of the Nobel Prize in 1983, said it is probably the most beautiful of all existing theories. So if we understand the stature of Chandrasekhar, we know what he means by that statement. So what's now new in this game of general relativity? Well, now the gravitational field is in the picture. You see, with special relativity, although we spoke about simultaneous events and so on, but there was no effect of gravity there. So it was still about light traveling in straight lines. However, now, Einstein realized that when a massive body is nearby, the massive body curves the space-time geometry around it. The net effect is that the photon of light doesn't pass harmlessly in a straight line past a large object. The gravitational field of the object bends the geometry around it so that the path it follows now is quite different. So this curved space-time needs a different kind of understanding. New mathematics is required, a new geometry, the geometry of curved space-time. And the field of differential geometry becomes totally relevant in this aspect. The field equations governing the motion or movement in such a setup are the Einstein field equations. Innocuously, they look like GAB equals TAB. So they look quite harmless in that version. But if you had to elaborate, the GAB is actually RAB minus half RGAB. I'll define these objects in a moment. This GAB is called the Einstein tensor. So the left-hand side here, you could say, is mathematics. The right-hand side, TAB, is defined as rho plus P. Rho is the energy density, P is the pressure, UA, UB, those are the velocity, 4 velocities. PGAB, the GAB, small GAB, is the metric tensor. So in this arena, we have a metric tensor involved. And the right-hand side is known as energy momentum tensor. So on the left-hand side, you have mathematics, GAB. On the right-hand side, you have physics, TAB. And Einstein himself is reported to have said that the left-hand side is a palace of gold. The right-hand side is a hovel of wood. So the left-hand side is like a palace. The right-hand side is like a hut, a small dwelling. So the mathematics side is quite safe. So one can do a healthy living in science by focusing on the left-hand side. But if you want to understand natural phenomena, then one has to also speak about the right-hand side. Therefore, I said early on that it's a mixture of mathematics and physics, a beautiful mixture of mathematics and physics. Now, what are some of the mathematical elements that underpin an understanding of gravity? We need the object called the affine connection. The affine connection is what guarantees parallel transport of a vector along a certain curve. To move a vector parallel to itself along a certain curve, the mathematical device required for that transformations to happen seamlessly, for the tangent spaces and the cotangent bundles to talk to each other covariantly and contravariantly, we need this object called the affine connection or the metric connection. This metric connection in general relativity is torsion-free. Torsion means the effect of twisting. We don't want these vectors to twist around as they are traveling along a curved space. So this one in general relativity is known as the Levi-Civita connection, and it allows us to work in coordinate frames called holonomic coordinates. Those are the bread and butter issues in general relativity. Normally, you don't need a metric when you have an affine connection in a manifold. But if a metric is available or the manifold is endowed with a metric, then a lot can be learned about the geometry and the shape of the manifold itself. So using the affine connection, gamma ABC, we construct what is called the Riemann Tensor, RABCD. This four-index object, written in terms of the metric tensor, these are called also the Christoffel symbols, or the affine connection, as I call it already, and some of the derivatives and products. Wherever you see, on the left-hand side, you got A, B, C, D, but on the right-hand side, you also have an E. That means you have to sum across E. So that's the Einstein summation convention. We don't use cumbersome sigmas. It's understood when a free variable appears on the right. Sorry, I don't mean to insult the audience, but I assume that the audience is general and they're experts from various branches of mathematics. So therefore, I explain things a little more carefully. It may not be that there are many relativists amongst us, but in any case, we hope everybody can benefit something after the talk is over. So using the Riemann tensor, we can perform a contraction of the Riemann tensor. The Riemann tensor encapsulates all the geometry of the manifold. It can tell you everything. In itself, if you work out its components, there's not much you can learn from each component, but contractions of the Riemann tensor give you the Ricci tensor in this form here. And then the contraction or the trace of the Ricci tensor, GAB, upper AB, is the metric tensor multiplied by RAB, the Ricci tensor, gives you R, which is the Ricci scalar. This is linked to the volume element when you construct an action for the equations of motion. Now, explicitly writing the Einstein equations, if we start off with a spherically symmetric spacetime, so the general metric is written like this, minus e to the 2 nu of r dt squared plus e to the 2 lambda dr squared plus r squared. This part here is the 2 ball, the surface of a 2 sphere. Okay? So if you use the metric components, so this is like G0, G11, G22, G33, and compute all those things, the gammas, the R, A, B, C, D, and so on, you will need a velocity vector UA, which is co-moving. That will allow you now to generate the Einstein field equations GAB equals TAB. This is now done very easily these days. In our days, without the use of computers, it will take us several weeks to reach this phase. But these days, one can do this in a few minutes using software like GR Tensor which works off a maple engine. So I'm quite sure nobody is going to pay close attention to these equations. But in any case, I just want to draw your attention to some of the salient facts, because these equations will evolve into something worse later on in the discussion. So if you look at the equations on the right-hand side, you've got rho r squared PR. That's a radial pressure r squared. P theta r squared, or the tangential pressure, or pressure in the direction of theta, you could say. So those are the three physical quantities, dynamical quantities: rho, density, pressure, and pressure. There's three. On the left-hand side, there are quantities like lambda and nu from the metric tensor. So on the right-hand side, you got the dynamics, and the left-hand side, you got the geometry, and you have to solve the system of equations. But now you will say, well, that's so easy. There's three equations, but there's 5 unknowns. So there's nothing to this. All we have to do is pick any metric you like, nu and lambda, any functions you can think of, you know, some linear function, a quadratic function, whatever, sine x, any kind of function, you make it up, plug that in here, and you'll be able to know what the density pressures are. That's true. However, that game is totally useless in general relativity, because you are unlikely to learn much. And I'll show you later on that there are certain conditions that I impose on the models which are unlikely to work if you work in a very random way of that type. In any case, if you're solving that problem, which is actually not a problem to solve, anyone can solve that, then that's what we call an anisotropic perfect fluid. In other words, the radial and the tangential pressures are different. In a static configuration, like we have at hand, there's no time dependence, you'll notice. The dash there represents derivative with respect to radius. So it's a static configuration. So it probably represents a star that's at equilibrium. So then it is reasonable for the tangential and the radial pressure to be equal. So there are no extra stresses involved in distorting the object. So if you do that, if you equate the pressures R, PR, and the P theta, then you will end up with a differential equation connecting the nus and the lambdas. And that's quite a horrendous differential equation. It is second order, but it's nonlinear. You see the nu dash squared here, and there's nu dash lambda dash. Of course, there's nu double dash as well. That's the highest order of the derivatives. That's the fundamental property of general relativity, is that the equations of motions are up to order 2. They never exceed 2. So later on, we will discuss modifications of the gravity theory, and that rule must still hold. You must never be able to go beyond the second order derivatives if you want to construct a theory of gravity. It's like a holy grail of gravity theory. So if you do that, you'll have a pressure isotropy equation. Then the game becomes interesting. So to find solutions of that pressure isotropy equation is not trivial anymore, although you might be observing that you still have 1 degree of freedom. Earlier on, it was 5 unknowns, 3 equations. Now it becomes 4 unknowns, still 3 equations. You still have 1 degree of freedom, right? So in general, you should have had 10 equations, but because of spherical symmetry, we assume spherically symmetric spacetimes, it boiled down to just 4 equations, right? They're partial differential equations, coupled and nonlinear, clearly very hard to solve. And how does one solve them? Well, throughout history, there have been many attempts to solve them. Einstein himself tried his hand at solving them, but he couldn't. He came up with he tried, the first thing to say was that let's assume that nu is a constant. Technically, that's what you do when you start off with a very complicated system. And he constructed a model which is now known as a defective Einstein universe model, because it turned out the pressure and the density worked out to be constants. So that's unrealistic. And also there were some negative signs there which are not required. So after that, there were many attempts. Now the attempts in solving them are largely ad hoc. In some sense, you take a fluke, a guess, or as the mathematics has been refined, one can build new solutions from old solutions. especially defective solutions, solutions which don't have the ideal properties, you may perform conformal transformations on these old solutions and generate new solutions that have good properties. You can also introduce physics. For example, you may assume an equation of state. Equation of state means relating the density and the pressure. Now the system becomes worse. Now that is the last of the options. Remember I said you have 4 equations and 3 unknowns? I'm sorry, 3 equations and 4 unknowns, 1 degree of freedom. So you have one more free choice to make, one wish as it were, as I tell students. If you use that wish to have an equation of state, the game is over. You will get nowhere. In over 110 years of the general theory of relativity, no one has ever found a solution with an equation of state, even the simplest equation of state, a linear equation of state. People have found solutions using other techniques like ad hoc methods, and later on discovered that an equation of state was present. The pressure is a function of the density. In other words, the pressure varies directly with the density without knowing what the radius is. So at any point inside the star, if you know the density, you know the pressure. You don't have to know what the radius is, how far you're from the center. That's what an equation of state entails. And then when all else fails, a lot of business has been done in the area of numerical analysis. So those equations lend themselves to various numerical schemes, and a lot of work has been done in that respect. The sad thing about that kind of work is that it's very rare that people actually ponder over the deep implications of numerical analysis, like error bounds and so on. And people just go headlong developing models without talking about the degree of accuracy of those models. Anyway, that is a fertile area that people have followed. Historically, 1916, Karl Schwarzschild found the first exterior metric where the density is 0. That's easy. Even university students, undergrads can do that. It's normally in a course on general relativity. 2 years later, Reisner and Nordstrom added an electromagnetic field to the game, and they found a solution for a charged sphere. A lot longer than that, in 1951, P.C. Vaidya, the famous Indian relativist, he found a radiating sphere known as the Vaidya shining star metric. These are the 4 classic solutions, by the way, in the literature. These are like folklore. And then in 1963, these are vacuum solutions, exterior solutions, which can be used to represent black holes. In 1963, Roy Kerr found the rotating version of the exterior space-time outside a sphere that's rotating. And this proved to be a very complicated system. In his paper, which was very short, 1 or 2 pages, he gave hardly any details. And up to this day, when he speaks on this topic, we still don't understand how he discovered it. But anyway, it's there. But there's a lot of insight has come forward in recent times that have illuminated us about how that solution can be found. But these are vacuum metrics, the famous ones known in science. What about the interior now? That's the exterior, the vacuum outside. Well, the game there is a lot tougher. The vacuum metrics, by the way, are unique metrics because the density is 0. And if you think back to the Einstein equations, the first equation, G0 does not have nu, it only has lambda. So it's always easy to find that, to solve, right? And it can also be written as a total derivative. That's why it's easy to solve for the vacuum. In 1915, Einstein, as I mentioned already, spoke about this defective model, which is not valid. In 1916, after finding the vacuum exterior metric, Karl Schwarzschild found the interior metric, which represented the metric for a constant density star, or what we call an incompressible fluid. Many years later, 23 years later, Richard Tolman of the famous Tolman-Oppenheimer-Volkoff team, part of that famous US experiment. Remember, 1939 is a critical year in human history in terms of the World War and so on. He reported 8 classes of solutions of the Einstein's equations for the interior of stars. static stars. And he made a very cunning rearrangement of the field equations, which is quite a brilliant observation. And as a result of that, generated these classes, and at least 2 or 3 classes of those solutions, beyond the well-known ones of Schwarzschild and Staffordji, rediscovered. They are non-trivial and they are useful in stellar modeling, even up to today. 10 years later, Riemann published a very important method of solving the equations, which actually fell by the wayside. People ignored the paper. And then it surfaced again in the 2000s. And everyone started to work on that. And of course, from the year 1915 till now, there have been about 120 exact solutions of Einstein's equations that have been reported. Very few of them, only about 10 of them, have any physical relevance. The rest of them are simply for academic reasons. And journals nowadays refuse to publish just exact solutions because they want the solutions to either be, to have some good properties physically, or the methods of finding those solutions should be something novel. Now, it might be useful for me to mention some unsolved problems in the history of relativity. The one enigmatic problem that's unsolved is to find an interior metric that matches to that 1963 Kerr metric. The Kerr metric, as we said, was reported in 1963, well over 50 years ago. And recently people celebrated that anniversary. But up till this day, no one has found a metric for the interior. So here's the statement of the Kerr metric, the exterior, the vacuum. You can see that it has got cross off diagonal terms, dt, d phi. And this rho squared is defined as r squared plus a squared cos squared theta. A is the angular momentum here. And the delta is defined as r squared minus 2mr plus a squared. You see a delta appears here. Right? When the delta is 0, so this thing becomes infinite here, that generates the new physics, black holes and things called horizons and singularities and so on, which is actually the interesting part of the entire game. Now, what is the reason why nobody has been able to solve the field equations that can match to the exterior Kerr metric? You see, when you find an interior metric, you have to match the interior with the exterior. Like if you find a Schwarzschild interior, it must match across a smooth boundary with the exterior. The matching is known as the Israel-Damoir junction conditions and has been found a long time ago. It's a simple case of matching the components of the metric tensor. But the Israel-Damoir theorem also shows us that the second fundamental form is equivalent to saying that the pressure becomes 0 on a certain boundary. But these three are not independent. There are only 2 independent conditions involved. But that matching has to be done. But so far, nobody has found a metric for the interior of a rotating sphere. They have found for a slow rotating sphere. If you take a certain simpler version, slow rotation, they call it, but not for the general case of arbitrary rotation of a sphere. The main problem, the mathematical problem, is that there is a phenomenon called frame dragging. So that Kerr metric that I exhibited a moment ago may also be written in this form here, GTT minus GT phi squared over that, blah, 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 blah. All of these, you still got your diagonal term here. It's impossible to diagonalize the Kerr metric. This is well known now. And when you write it like this, what this shows is that this is equivalent to a co-rotating reference frame that is rotating with an angular speed of omega. And it depends on the radius r and the co-latitude angle theta. So what that means is that, you see, in a normal setup, you might have an object sitting in a background, and you want to do measurements of that object. But now, if you are doing measurements of an object and the background is also moving with the object, that's forced to happen, you see, according to the way the metric is written. If an observer gets close to the spinning star, or black hole, if you want to call it that for now, then you become entrained by that rotation. So you can't help it, but you will be moving with that object. So the mathematics of those two systems, that mathematics is not in place yet. And that's one of the biggest stumbling blocks to finding the interior of the curve metric. You see, this is a case where I think where the mathematics hasn't kept pace with the physics. So therefore, I mean, not the physics as such, but the fact is that we don't have the mathematics in place. It may come into place shortly. With the advent of computing, things are moving quite fast in these days. So we expect that kind of problem to also yield in due course. So for now, there's no sign of an interior metric. That metric of Kerr we mentioned has got two interesting surfaces. Remember I said when things become zero, you get infinity and so on. One is the inner event horizon, and the other is the ergo region. That's a region just outside there. And neither of these is an essential singularity. You see, mathematically also, if you look at the Schwarzschild metric as well, it has a singularity at r equals to 2m, the famous black hole. And mathematically, it has been shown that these singularities are removable. They are coordinate singularities, as opposed to curvature singularities. Coordinate singularities can be removed by an appropriate choice of coordinate systems. So this has been done already, and it's well known in the field. But as I said, for this particular case here, oh, by the way, those coordinates are called Kruskal-Zekeres coordinates. Kruskal-Zekeres coordinates that provide a continuation of the metric field in such a way that the singularities can be removed. There are ways of testing whether a singularity can be removed or not. We calculate certain scalar invariants, such as the Kretschmann scalar, and there are 15 others that can give us an idea of whether a singularity is removable or not. So you see some deep mathematics is involved there. By the way, I skipped an important point here. If I just go back, when we speak about the boundary, what is a boundary? This is also a questionable thing in the stellar structure understanding. If you think of a boundary, if you think of an orange has a peel around it, and then there's another space that comes after that. So is that what a boundary is? Is there something very thin that exists on the surface? What do you mean by a boundary? So this has been an aspect questioned a long time ago by famous names in relativity like John Wheeler and others, and they then began to speak of a concept of a boundary of a boundary. And sometimes in some papers that I've written on gravistars, which consist of multi-layer fluids, we make use of certain things that can give us like a error function in statistics that can represent a small increment. Right. So these things are well studied in the science. Exact solutions of the Einstein equations are very important because they allow us to model stars. We can get to know what's happening inside the stars. You see, for example, the stars could be connected with the nucleosynthesis, the formation of elements. In order for two hydrogens to be pushed together to form a helium, you need a very strong force. Where do you get such forces in the universe? So these kind of forces you get inside neutron stars, black holes, and so on. The neutron star density is 10 to the 13 gram per cubic centimeter. That's a lot of material in 1 cubic centimeter. 1 cubic centimeter is like a block of sugar. Think about having 10 to the 13 grams in 1 teaspoon of sugar. It's not a good proposition to try to pick that up. So all these stars are important. They tell us much about the physics. General relativity as a theory has been highly successful. I won't go into the details here because they are well known, colloquially. The perihelion advance of Mercury was explained with the general relativity. The deflection of light by the sun was studied through the use of eclipses and so on. Gravitational redshift, all these kinds of things are well known. So general relativity is a well-studied and an accurate theory that serves us well. One of the predictions of general relativity was gravitational waves. That was predicted by Einstein. He used a weak field approximation and showed that the box function equals to 0. The box function is the D'Alembert operator, and that is actually a wave operator. So that equal to 0 gave a wave equation, and that was a prediction of gravitational waves would exist. But it was a conjecture for almost 100 years. And on 14 September 2015, there was the first detection of the gravitational wave by LIGO called GW150914. And in 2017, they were given the Nobel Prize for that, the team. I might point out to mathematicians also LISA. This experiment is to come in the future, but this LISA experiment is a space-based detection of gravitational waves. It consists of an equilateral triangle floating around the sun, as you can see in the picture there. And the arms of that equilateral triangle are 2.5 million kilometers long. Right? That's quite a big distance. That's why you can't do this experiment on the Earth. But this is floating around, this will float around the sun, and they'll try to keep those arms in the shape of an equilateral triangle, although it's impossible, because at each of those points of the equilateral triangle, they have 2 receivers that watch the other 2 points. So a total of 6 coordinates are required. And to keep those things, in other words, quiet, in other words, to cancel out certain noise, this word noise is used in the context of these experiments, you are required to solve some complicated equations. And Professor Sanjeev Durandar from IUCAA wrote a famous paper in 2010 or so, where he used commutative algebra and algebraic geometry methods to solve that problem for various configurations, approximately, but it's quite accurate. It turns out that with the 3 of those objects working, you need a polynomial of order 23. It's of the type 8n-1, depending on how many objects are there. Interesting to read on that. Coming back now to black holes. This was a prediction by Einstein, simple prediction that comes out of his of the Schwarzschild exterior metric. R equals to 2m, you can see is the problem. That tells you that there's something happening there. The Horizon Telescope recently reported this famous picture, and they found what is called a shadow of a black hole, because by definition, a black hole is an object that you can't see. That's very convenient for physicists to invent an object that you can't find. But anyway, an indirect way of seeing it is through its shadow. So the idea is that photons of light that pass near a black hole will either be deflected away from it, will either be sucked into it, or the third option is that they can float around in a ring around it called a photon ring, which you would see. And that's exactly what was observed. Well, actually not observed. What they did was they set up a system of radio telescopes at 8 different locations, or 7 locations on the Earth, collected data from these, and then they flew all these data points together to one point in hard drives that were like petabytes of data, lots of data. A petabyte is what? 1,000 terabytes. And then they sewed all the data together using Fourier analysis methods. I think fast Fourier transforms. And then they got that picture that you see. It's famously displayed there. And in the year 2020, Sir Roger Penrose received a Nobel Prize for the discovery of black hole formation. Prior to that, it was just a figment of our imagination. But now it has been amply demonstrated. I wonder whether people should not consider giving Einstein his 2nd Nobel Prize for the general theory of relativity. For a long time, they said that, where are black holes and so on, but now we have them. So the person who really had the foresight was Einstein. Now, the weaknesses of general relativity is that it doesn't explain what we observe around us completely. The universe is known to be expanding, accelerating and expanding. That doesn't follow from Einstein's field equations. So how does one resolve that? One avenue is through physics. People have conjectured that there must be some fluid called dark matter or dark energy that has a negative pressure that is driving expansion, cosmic expansion. That's one way. But then the alternative could be, just before I say give you the alternative, James Peebles won a Nobel Prize recently, and he actually argued that the the general theory of relativity, as good as it is, it works in the solar system test, as we've discovered. It also works in the galaxy, the Milky Way, because of that black hole discovery. But why should we assume it works in the whole universe? So that opens up the way for alternatives from dark energy and so on. We will ask the question whether, is it not possible that the answers lie in a new theory of gravity that goes beyond Einstein? That's what we think. That's my idea also. And could it be the geometric sector needs to be modified and that Einstein's left-hand side is not adequate? So we need to generalize Einstein's theory, modify it to take into account what we actually see around us. And it makes sense according to James Peeble, because we know that the GR works very well locally in the solar system and in the galaxy, but what about the universe is so big? Why should we expect it works all over? So it makes sense that there could be a room for modifying the general theory of relativity. If you do so, though, the basic ingredients involve diffeomorphism invariance. In other words, the laws of physics should not change from point to point, or it should not depend on the coordinate choices that you make. It should be universally valid. That's diffeomorphism invariance. The Bianchi identity should be satisfied, and you should be getting second order equations of motion. If you get higher than that, then you call that ghosts. The theory starts to become haunted by ghosts. That's what they say in the area. And of course, since we know Einstein's theory works well, you should be able to regain Einstein's theory in an appropriate limit of a solar system, for example. So you can't just make up anything you like. It has to satisfy these ideas. So Einstein himself came up with a thing called unimodular theory, but I won't go into that because of time, where he kept the volume element constant, the R, that is the Ricci scalar, right? And then there have been other attempts, f of RT theory. Maybe the action has to be written in this form here. Harco proposes. The problem with this version here is that there's a violation of energy conservation. The laws of energy conservation don't work anymore. What that means is that there's a net production of energy. You expect energy to be balanced in the universe, or if you're producing energy, it must go somewhere. But these theories don't have that. Their argument is that with curved space-time, why can't such a thing happen? So there could be a net production of energy. That's the argument used in these papers. Rastel's theory also in 1972 came up with the idea that the energy momentum tensor, the covariant derivative of it doesn't vanish, but it's simply proportional to the derivative of the Ricci scalar. You see, according to him, that's really what the Einstein field equations in general requires, not that it becomes zero. In Einstein's gravity, the right-hand side is zero. Alpha is zero here. The energy momentum tensor, this TAB, the covariant derivative vanishes. Okay? And so the field equations in this case here are written like this. It's a modification, but it has some downside. What we are punting these days is what is called Lovelock gravity. David Lovelock in 1971 was a student at our university here in Durban, the University of KwaZulu-Natal, and he worked with the famous Hanno Rund, whose textbooks in applied mathematics are quite famous worldwide. He's supervisor here at our university. And they came up with a most general Lagrangian, a tensor Lagrangian that will produce only up to second order equations of motion. So in the normal case, the Einstein-Hilbert action is given by this S equals to 1/2 kappa, R root minus G. G is the determinant of the metric. I mean, this is the standard Einstein-Hilbert action. Curiously, Einstein names come first because Hilbert insisted that Einstein had done the heavy lifting, the original work, whereas Hilbert, the great mathematician, provided the mathematical workings underneath the bonnet. But it was Einstein's sharp-wittedness that saw the connections between all the parts. It's quite a humbling thing to contemplate. But you can modify the action as follows to give you the Lovelock tensor. which comprises alpha n, this is script GNAB, and goes from naught to the floor function of d minus 1 over 2. Lagrangian has a form alpha n r to the power n. So I have done a lot of work in this area. This is my area of specialization. The Lagrangian has this form here. This Rn, script Rn, is given by this formula here. It's a product of the Riemann tensor. These are Riemann tensor components, a normal Riemann tensor. And the Kronecker delta here is the generalized Kronecker delta given in this form here. You can use a big matrix to expand that. It has values 0, 1, and minus 1. Right? So this Lagrangian, believe it or not, gives you second order equations of motion. It is not haunted by any ghosts. So it works very well. Okay. All right, before I go further and end off, people have questioned whether higher dimensional theories are worthwhile to consider. Well, we don't know if there's no higher dimensions exist or not. Experiments have been conducted, but they've come up with no conclusive result. So we continue to work with these higher dimensional theories, pure Lovelock, Einstein, Gauss-Bonnet. They're known to have very good mathematical properties, and they are known to reduce to general relativity in the appropriate limit, right? I'll go a bit fast to end off. These are the Einstein-Gauss-Bonnet field equations. It's a special case of the Lovelock gravity. The parts that you see in green box there, that's the Einstein part, but the other parts there are the contributions from the Gauss-Bonnet term, which makes the field equations much more complicated, but not more than second order, right? So the exterior space-time is this Bolwer D-symmetric. When you find an interior metric, you will have to weld it with the exterior space-time as shown here. Right? And these are the exact interior metrics that have been reported in the literature. Most of them are by ourselves in our work. Right? There's some other related results. Some people have got the idea that we can reduce. You see, normally this is the 5-dimensional, 6-dimensional theory, but people have thought that by a dimensional regularization procedure introduced by a certain Tomazawa, we can actually consider this in a 4-dimensional setting. But unfortunately, time doesn't allow me, as my time is officially up. I'd like to stop here because the rest of it is about how the model is constructed. Thank you very much.
Thank you, Sudan. That was a really fascinating talk, and I can see the teacher background. You made a topic that really is quite complex, very understandable, although you couldn't quite hide the fact that you work with quite horrible equations. I would like to just invite the audience in the venue and also online if they have any comments or questions to you.
Online participants can raise their hands.
Yes.
They are in doubt.
Okay, I couldn't hear. Did you say there is a question?
It's very close to dinner time, so I guess questions may be few.
Well,
in India, that is.
I have a few, so they still have to wait. So, Sudan, I don't know much about this topic, but I really found your talk clarified a lot of my questions. But what I'm still left unsure about, so you explained about extensions of general relativity, but then there's quantum mechanics. And if I understand that correctly, that has to do with a different interpretation of time. Could you just briefly maybe just put that into the perspective of your talk?
Yes, quantum field theory is the study of the very small objects, like the atom and what happens inside the atom. So yeah. Small objects like protons, neutrons, and so on, subatomic particles. Whereas general relativity is the theory of the very big objects like stars and galaxies and the universe. Once I was at a conference in 2005, it was Einstein's centenary in Paris, and one of the speakers there was a Nobel laureate, and he said something quite profound. He said, assume you are a giant and you are looking down upon the universe. if you're a huge giant, to you, the universe will look like what the inside of an atom looks like. You know, to a giant, what we consider as humans to be huge could be actually small. So therefore, he said that there should actually be a grand unified theory which works for this very small objects and very big objects. So this grand unified theory has been the most elusive searches for the past 100 years now. We haven't been able to connect quantum field theory with general relativity. There isn't a direct correlation. There are many problems. One of the problems, though, is something which I'm working on here is the dimensional shift. In quantum gravity, you need dimensions of order 10 and 11 and higher. Whereas in general relativity, everything is taking place in a 4-dimensional manifold. That's what we can actually access. But with this new Lovelock idea and Einstein Gauss-Bonnet theory, it allows us to work in higher dimensions. So now we have a foothold to perform some kind of, connection between the two. So that may be promising going forward, but I think we're still a very long way off between unifying the two worlds, as it were. I hope that gives a little idea.
Yes, yes. So there's some questions in the chat. V. Governed has asked if singularities can be removed by coordinate choices. Are they physically real?
Well, you see, mathematically you can remove them, but that's because of coordinate extensions of the space-time. Sometimes they're irremovable. Many times they are. So when they are irremovable, then they are definitely physically viable. And the singularity in the space-time, the Schwarzschild metric that we mentioned earlier on, is a classic case of a black hole. At r equals to 2m, you have an event horizon. That horizon blocks everything from the inside. So from the inside, you can get no information to the outside world. Anything that comes near it gets sucked into it. So that's a very real object. We now know it's real because they've reported the so-called shadow of the black hole. So it is believed there's a black hole at the center of our galaxy, the Milky Way, but that's not the one they reported on recently. The 178701 that they reported is somewhere closer by. I can't remember the exact name of it. There's some description of it. But in any case, we know now such a thing exists. So in some instances, you can remove the singularities. Other cases, they're not removable. They are actual real. They are called curvature singularities, and they are persistent.
Okay. All right. So there's another question from Sharon. There have been other theories of gravity like the scalar field theories and modified Newtonian theory. Can you briefly discuss how they differ from general relativity?
Okay. Yeah, you have these scalar field theories. They are more applicable to cosmology. What I am interested in is astrophysics, relativistic astrophysics, stars. But these theories, scalar tensor theories and pure scalar theories, like the Brans-Dicke theories of the 1960s, on the right-hand side, they have a scalar field. If you remember, I said there's a left-hand side with GAB, that you can't play with. But on the right-hand side, TAB, we normally have a tensor, the metric tensor GAB incorporated there. So we normally have a tensor field. But on the right-hand side, you can also have anything. You can have a scalar field, let's put it that way. So then you can use that to find the dynamics of the object as well. So that's quite different. And I think that's more applicable in cosmology, not so much in relativistic astrophysics. The modified theories, and we are actually trying to modify the theory ourselves. We are going beyond, you are talking about the modified Newtonian theory called MOND, M-O-N-D. I don't know much about it, but as you described it, there are modifications of Newton's theory appropriately. It's all in the game. The game is big. Even the modifications I discussed here are only a small subset of modifications you can make. But at the end of the day, as I said in one of the slides, you must come back to certain ground-based realities, and that is you must have up to second-order equations of motion. Like you see the scalar tensor theory called F of R theory. It's very useful in explaining why the universe is undergoing accelerated expansion. It succeeds there, but it fails because it has fourth-order derivatives. So it gets thrown out on those grounds. So people don't accept it. Although it works in one aspect, it fails in another area. So you need to be self-consistent entirely, and at the end of the day, regain Einstein's theory in the local level, as it were.
Okay. All right. So I had another question, but I think I'll ask it to you privately because it's sort of a bit more specialized. Because I noticed that some of the equations are nonlinear second-order partial differential equations, and I was wondering whether there's any connection to Pan-Nové equations. But I suspect that answer, you could either just say no, or else maybe we should discuss it at some other stage.
No, the answer is no. There are many people who have reduced the equations to Pan-Nové analysis, especially my friend Kesh Govender, Peter Leach, my colleagues. Yeah, they published lots of works on it. You see, when you reduce the equations through some kind of assumptions, then you water the problem down. So that's why the ad hoc methods are a little more successful, because you begin to study some kind of scenario that may not be realistic. In other words, you're trying to get the equation to something you know, which is well understood. Now, through various coordinate transformations, we can make the Einstein equations also quasi-linear. The main equation can become second-order linear. In fact, we have been doing a good trade in that even the Lovelock equations can become quasi-linear with a suitable transformation. So the benefit of that is that we are now, on a firm footing. There's a well-understood theory of linear differential equations of any order as such. Basically, they boil down to algebraic equations, and if you can solve an algebraic equation, then you might have some hope of solving the linear differential equation, although it's a far stretch, but that's really what it boils down to.
Okay, thanks. Let me give the audience, the live audience, one more chance. Are there any questions from that side or comments? All right, so dinner.
Yeah, are there any questions from the audience? I don't think there is any.
Okay, good. All right, so then it remains to thank you again, Sudan. This was really a close to perfect plenary talk. You were right to do it general, because I'm not a specialist and I know many people aren't, and it was very interesting. Thank you very much. Goodbye.
Thank you. Bye-bye.
I would like to thank Dr. Hansraj again for delivering the last lecture of today. And this also marks the end of day 1 of the conference. And tomorrow, the day 2 sessions for day 2 will begin again at 9 a.m. IST. So thank you everyone for joining us for the first day of the conference. And we'll go now for dinner and we'll meet again for tomorrow. Thank you.
Bye.